In this video, we'll be looking at some of those extra key terms that we need to understand our measurement instrumentation systems. The first one we look at is range. What is the range? Well, what we think about when we look at range is we look at what is the input range of a particular sensor and also the output range. Now, the output's normally in a voltage, so maybe 4 millivolts to 20 millivolts or something like that. Or maybe it's 0 to 5 volts. It depends on the actual sensor. Now, the input range is in whatever quantity we're trying to read. If we've got an accelerometer where we're measuring G forces, it might be plus or minus 2G. If we're reading pressure, it might be from 0 to 1,000 pascals. It just depends on what actual physical quantity we're trying to read. If we're measuring temperature, our input range might be 0 to 45 degrees, or it might be like minus 30 to plus 60 degrees. Just depends on the sensor that we're working with. Where we find this range? Well, we look at the sensor data sheet and it should specify, just like this sensor up here, the range is from this to this. Now, it's important to note, if we try and measure something outside of that range, like we've got our sensor and our sensor might be rated to 60 degrees Celsius. If we try and measure a temperature that's 70 degrees Celsius or something, where our sensor's saturated, which means that it's beyond the normal measurement range that it can measure at. During our normal operating conditions, we don't want our sensors to be saturated. So we try and keep our sensors suited to the measurement ranges that we need. Now, it's important to differentiate between our sensor range that we can measure over and the absolute maximum value that the sensor can receive. The absolute maximum value the sensor can receive is typically longer and larger than the range. So for the accelerometer, our next term is the span of a sensor. And a span is basically just the maximum range that the sensor can take minus the minimum range it can take. So what's the difference between them? It gives us the maximum variation of our input to this particular sensor. So, for example, for our pressure sensor, if we could measure from 10 to the 4 atmospheres down to 0 atmospheres. So for our pressure sensor, for example, if we could measure from 0 to 10 to the 4 pascals, we've got 10 to the 4 minus 0. Our span of the sensor is 10 to the 4 pascals. Likewise, you can do it on the output, or if you've got an accelerometer, and we saw just in the previous slide that example that went from minus 2Gs to 2Gs, that would give us a span of 4 G forces. Our next thing to consider is the linearity of the sensor. And basically here, what we're trying to do is it's highly desirable for us to have a sensor where the output is linearly proportional to what the input is. So we increase the input by a certain amount and the output will increase by a proportional amount to what we increased in. We don't kind of want this sort of thing going on where it's going up or down. That's what we call a non-monotonic sensor or characterization of it. We want something that's nice and monotonic, so as we increase it, it goes up. And if we have it nice and linear there, it'll be nice and easy to characterize it. Back from high school maths, we learned about linear functions. We had the old y equals mx plus c sort of thing. And so we've got two different things that we're playing around with here. We've got our input, which is where we'd normally have the x. We've got our output, which is where we'd normally have the y. Then we have our gradient. In this case, we call the gradient k. The gradient's that slope there that will allow us to adjust what we'll later call our sensitivity. And then we've got our intercept, or where it crosses the y-axis, and that's what we call A. So what we normally do is we characterize our sensor. We'll take a bunch of different measurements at different inputs. So an input for a temperature sensor at 0 degrees and 10 degrees and 20 degrees and 30 degrees and 40 degrees. And we look at what the output of the sensor is at each of those inputs. We can then plot them on a graph and draw a line of best fit through them, either using Excel and we use the linear trend line function, or we use MATLAB and use a polyfit to add a linear polynomial through there. And that allows us to draw that line of best fit so we characterize our sensor. It will normally give us an R or an R squared value as well to tell us how well our linear approximation is based on the actual data that we've got. If the R squared value is quite close to 1, like 0.9 or 0.95 or something like that, we've actually got a pretty good fit for that linear equation that we're using to characterize our sense. When we talk about non-linearity, the opposite to linearity, we're looking at the spread of those points from that linear line that we've got there. So how much deviation do we get in our measurement values from that linear line? And normally this is quoted as a percentage away from our sensor span. So for an example, just above on non-linearity, we have our linear line there, we have the actual sensor measurements or readings there, and we can work out by measuring them, the greatest amount of non-linearity we've got is 2 millivolts. Well, our output span that ranges over is 100 millivolts. And so we can say, okay, so we've got maybe 0 to 100 millivolts. So we can say then our non-linearity across the whole range, across the full scale of that span, is 2 millivolts divided by 100 millivolts times 100%, which gives us a 2% non-linearity. When we're doing these sort of non-linearity calculations, we're looking for the worst case non-linearity that we actually see in our system. Now, the final term that I'll define in this video is the one of sensitivity. And the sensitivity is basically a measure of that gradient that we saw that characterizes our linear equation or our characterization of this sensor. So we're looking at how much the output will change corresponding to a change in the input. So if we divide the change in the output divided by the change in the input, it'll give us our sensitivity. So for example, say we had a thermistor that increased by 14 ohms as we increase our temperature by 40 degrees. So we say 14 ohms divided by 40 degrees gives us a sensitivity of 0.35 ohms per degree Celsius. So as I said before, this is related to that line of best fit, of that gradient that we have as we characterize our sensors.